most of this research is being done under a grant through the Aviation Sustainability Center, or ASCENT, which is a program that funds research looking for solutions to the aviation industry's biggest challenges, specifically around sustainability and environmental progress. Penn State is involved in this on 2 different levels under this grant. I'm working with the center under Laura Fowler, who's the Chief Sustainability Officer at Penn State. We're involved in the law and policy side of things, also doing some work on soil organic carbon and carbon capture and sequestration. That team is listed here. So we'll be incorporating some of that research into the presentation I have today. There's also another entirely separate piece of the work that's being done at Penn State that, quite frankly, I know almost nothing at all about. There may be people in the room or on Zoom who know more than I do. So you're welcome to chime in, but it has to do with noise research, and it's also being funded through ASCENT. And this is, again, a major initiative happening at Penn State, and we have some of the people involved in that on the screen here. Just wanted to acknowledge that. Okay. So today, what I'm going to do, hopefully, for any of you who are intimately familiar with sustainable aviation fuel and this whole process, the first part of the presentation is probably going to be a review for you. I want to make sure that people who aren't involved in this, because I do think that this is an area, as Seth said, that it doesn't get a whole lot of attention other than as you're getting on a United airplane and you see the Oscar the Grouch cartoons. That's probably the place you see it the most. It's not a space that people are thinking a lot about necessarily. So I do want to talk through the challenge and some of the issues that we're trying to work through as part of this problem. Talk about what SAF is specifically, talk about the technology, talk about where it comes from and what some of the challenges are, both on the technical side of things, on the feedstock side of things, and then we'll finally get through the economic challenges. And that's where I'll start talking about some of the law and policy research that we're doing and some of the different policy solutions that are out there and being considered as we go through that. Okay, so we'll start by talking about the challenge. And again, this part is something that I think is generally familiar to most of us, right? We're trying to decarbonize all of the industries, to the extent that we can. And the airline industry is a big one. In 2019, the estimate is that passengers flew approximately 5 trillion miles. To put that in the astronomical perspective that it really fits into, 5 trillion miles is almost an entire light year. A light year is about 5.9 trillion miles. So in 2019, passengers flew almost an entire light year. So this is a pretty significant industry. Again, not that I needed to tell you that, you know that intuitively. But it's grown significantly, and it's projected to continue to grow, as I'll talk about on the next slide. But between 1990 and 2019, aviation grew by approximately quadrupled, and that's both in passenger miles flown and the amount of freight that's being flown as well. So just growing, again, almost on astronomical levels. That said, because of increased performance, operations, efficiencies that have happened, even though essentially the amount of air travel that has happened over the course of the last 30 years or so has quadrupled, the amount of greenhouse gas emissions from the aviation industry has only doubled. Now, only is kind of a loaded word in that context, but you can see that there has been some progress that's being made. So in efficiency and those sorts of things. So again, this chart is showing carbon dioxide emissions going back through history. But if you look from 1990 through 2019, it's only approximately doubled, as opposed to quadrupling, as you might expect, given the amount of volume that's occurred. 2019 was selected intentionally as a reference point for some of those conversations because, as you all are, again, familiar with or can guess, the amount of air travel dropped precipitously in 2020 as a result of the global pandemic. It's slowly inching its way back up. The expectation is that this year, 2024, air travel will get back to the peaks that it had in 2019. So we're back to basically where we were in 2019 after dropping off for a couple of years. Given that, where we are today, aviation contributes about 2.5% of global carbon emissions, which again is a significant increase from 2010. So if you look back at let's just keep it here. But if you look back at the amount of emissions that are happening, the amount of emissions kind of went up linearly over the course of time. Here, if you're looking at the share of global greenhouse gas emissions, you can see it's starting to spike, or at least the slope of the graph has increased significantly starting in 2010. And that's not because of anything that's happening specifically in the aviation industry. that's really a reflection of the fact, this is a share of total greenhouse gas or carbon dioxide emissions across all industries. And this increased slope is actually more of a reflection of the fact that other industries are starting to decarbonize a little bit faster than aviation, which really, aside from some increases in improvements in efficiency, really hasn't been able to make much of a change. In addition to the fact, and this isn't something I'm going to talk a lot about today, I'm going to be focused primarily on carbon dioxide emissions, but it is worth noting that the overall impact from the aviation industry is bigger than just the impact from greenhouse gas emissions specifically, because of some of the other things that are released as part of the aviation process. Soot, contrails, those are the jet trails that you see in the sky. Those all contribute to climate change impacts as well. There are actually some positive, some negative, but when you balance them all out, the total impact is actually kind of increases the impact from aviation travel from the 2.5% that you would expect simply from greenhouse gas emissions to about 4% of being responsible for about 4% of global warming to date. So where are we going in the future? Obviously, the future is impossible to predict, but this is a projection from Bain & Company. It projects that global aviation will increase from 2019 levels, which again are about today's levels. So between now and 2030, they expect an increase of about 36%. So that's, again, pretty substantial growth just over the course of the next 6 years in the aviation industry. And obviously, depending on the economy, depending on any number of factors, that can change up or down. And as a result of that, even though we're going to talk about a host of mitigation measures that the aviation industry is trying to take, even with those measures in place, the greenhouse gas emissions from the aviation industry are projected to increase by about 3.5%. So even with the work that's being done, there's still a projection that greenhouse gas emissions will increase. Interestingly, and this comes from the same report, Bain says that in order, again, based on its projections, according for the aviation industry's greenhouse gas emissions to remain approximately constant at 2019/2024 levels in 2030, they estimate that a carbon tax equivalent of about 5% of the average ticket price would have to be added to the cost of fuel. So that's approximately the effect if one of those policies were adopted, which I'm not suggesting that it will be. Okay, so despite all of that, despite all of the increased emissions that we're talking about, despite the growth of the industry, and despite several sort of wide-ranging projections on what is to come, there is wide agreement on one thing, and that is a goal of net zero by 2050. And this is a goal that's been adopted by both international government organizations, the International Civil Aviation Organization, ICAO, if you're familiar with it, which is, we'll talk more about it later, but it's part of the United Nations. But they have 184 member states, so it's a goal of those government organizations. And it's also the goal of the major aviation trade airline, which is the International Air Transport Association. They represent 330 airlines. Both of them have set identical goals of achieving net zero in greenhouse gas emissions by the year 2050. And the US government hasn't quite said, again, they're part of ICAO, so they've adopted it implicitly as part of the ICAO program, but the US government's description is slightly different. They've adopted a SAF Grand Challenge, and the goal, which I would argue is consistent, at least with net zero by 2050, is to achieve 100% sustainable aviation fuel penetration by the year 2050. So to entirely replace petroleum-based jet fuel with sustainable aviation fuel, which is what we're going to be talking about today, by the year 2050. So how are we going to get there? As Seth mentioned, this is a challenging industry to decarbonize, right? We know we can't just plug in an airplane and fly it across the country. That would be a ridiculously long extension cord. So we're not going to be able to do that. Batteries are probably not going to be a major solution for us either, just because of the weight to energy ratio of a battery is going to present a challenge, especially for long haul flights. I was on a webinar just last week where a representative from United was talking about the fact that they think medium term, they may actually be able to replace some short-term flights, think Washington, New York to Boston, those sorts of flights. In the medium term, they think they may be able to fly electric planes on some of those shorter routes. So it's not that there can't be any electrification in this industry, but it's probably not going to be a major solution, and certainly not anytime in the short time horizon for long haul flights. One of the other challenges in the airline industry here is even if tomorrow we were able to adopt a really lightweight battery with almost unlimited energy, that theoretically could allow us to electrify using batteries over a shorter time span, that would still create economic problems within the airline industry. Because unlike the car industry where there's about a 12.5-year turnover with people replacing cars, so the average car has a life of about 12.5 years. In the airline industry, it's more like 30 years for an airplane. So either you'd be in a situation where you're continuing to run these planes for the next 30 years, or you're going to force the industry to adopt a very expensive replacement of their fleet before the depreciation table suggests that they should, which obviously creates economic problems. So what are the strategies? Aircraft improvements, operational optimization. I'll talk a little bit more about that on the next slide. And finally, low carbon fuels, which is what we're going to be focusing on here today. So this is a chart that comes from the airline industry. Again, this is IATA, International Air Transport Association. This is how they say they're going to be able to get to net zero by 2050. So they're saying 3% through infrastructure and operational efficiencies, another 13% through new technology, electricity, hydrogen, those sorts of things. Again, one of the things I've heard recently, and you can see kind of the scale of what we're talking about here, but one of the projections is that they can reduce jet engine idling time during loading and unloading of an airplane by leaving the jet engine off while the plane is loading, using an EV essentially to tow the plane back to the jetway and then let the jet turn on its engines at that point and initiate. So again, you can see where there would be some emission savings there, but probably not enough to get us anywhere close to a net zero kind of situation. The biggest part of this pie, obviously, and it's what we're going to talk about today, is sustainable aviation fuel. But even, and I didn't dig down deeply enough into these projections to see exactly what they're thinking the penetration rate will be of sustainable aviation fuel, but I suspect that they are assuming something close to 100% adoption of sustainable aviation fuel by 2050. And even with that, they're still going to need to do more. Offsets and carbon capture, you can see that here too, right? There's still going to be emissions, and as we'll talk about, the reason for that is that sustainable aviation fuel, despite the name, isn't zero carbon. There's still carbon emissions associated with sustainable aviation fuel, and they can vary depending on the technology and some of the other inputs that we can talk about as we go through, but it's almost impossible for it to be net zero anytime in the reasonably near future. So that does mean that there will still be a need for carbon offsets, carbon capture and sequestration, and those sorts of technologies. Okay, so that was just the general challenge the airline industry is facing. So what is sustainable aviation fuel, the thing that I've teased as being a pretty big part of the solution to that challenge? Disclaimer, it's not bacon and donuts. We're not going to just be able to put food waste directly into the engines of the planes and take off and fly to Honolulu when we feel like it. What it is instead, it is aviation fuel, right? Chemically speaking, it is very similar to, if not, it's not identical. It's nearly identical to the jet fuel that's being used in planes today. The big difference is that it's coming from some sort of renewable sources, renewable feedstocks, as opposed to a petroleum feedstock. And we'll talk more about some of the similarities and differences as we go through. So basically, you can consider it, again, it's a hydrocarbon-based fuel, which means it's considered a drop-in fuel. And this is a very important aspect of sustainable aviation fuel in order to qualify under the ASTM guidelines to be an approved sustainable aviation fuel. It has to be drop-in, which means that it can be put directly into airplane engines today. You don't have to do anything to retrofit the engines. You don't have to do anything to change the fleet of aircraft. You're going to take this fuel, you're going to put it directly in the same engine. You're not going to need to change anything about the aircraft itself. But in order to to be considered sustainable, obviously, there has to be some benefit in terms of reduction in greenhouse gas emissions. So on a life cycle basis, there are different definitions, and we'll touch on a couple of those as we go through this presentation today. But generally speaking, in the United States, the minimum threshold is about a 50% reduction in greenhouse gas emissions over the life cycle of the fuel itself. And we'll talk about some of the different feedstocks that can be used to produce sustainable aviation fuel. There are multiple pathways, and we'll talk about those as we go through, but lots of different possibilities. So again, because this is drop-in fuel, we're going to burn it in a jet engine the same way we would burn petroleum fuel. That means that if you draw a mass balance around the airplane and try to figure out, what's the difference in emissions, in greenhouse gas emissions from the airplane, you're not going to see much of a difference at all between petroleum-based Jet A and some of these sustainable aviation fuels. So in order to effectuate the greenhouse gas reductions that we're looking for, we're going to have to consider sustainable aviation, the life cycle of the fuel, of sustainable aviation fuel. And obviously you can see that that includes a lot of steps, including transportation, sorting and processing, refining, manufacturing, production, those sorts of things that are inherently likely to contribute to greenhouse gas emissions, right? Most of those processes, you can imagine as they're operated today, release greenhouse gas emissions. So most of the negative part of this formula, anything where we're talking about reducing greenhouse gas emissions, is likely going to have to come from the source, the initial source itself, the feedstock, whether that's from waste or biomass or taking carbon directly out of the air. That's where we're going to need to see the changes. So I put this chart up here. This is a little bit more detailed than I want to get into, but this comes from ICAO, again, the International Civil Aviation Organization. It's just a summary chart of the 8 different approved pathways for SAF, Sustainable Aviation Fuel, SAF. I'm going to use that acronym throughout the presentation today. But just putting it up here, a couple things I wanted you to take away. First of all, again, there are 8 different approved pathways. These pathways are approved by ASTM, which is the organization formerly known, I guess, as the American Society of Testing and Materials. And these processes are actually pretty substantially different if you dig down into them, and I'm not really qualified to do that. But if you look into the science and the engineering behind them, these are quite different processes, which means that they start from very different, or at least have the potential to start from very different feedstocks. Some of them use esters and fatty acids. That's primarily the HEFA process, which, as we'll talk about, is the HEFA stands for hydroprocessed esters and fatty acids. That's the process that's been used to generate most of the SAF that's been generated so far today, to date. But a lot of the other processes can use other feedstocks, biomass, sugars, municipal solid wastes, and things like that. The one at the bottom of my bullet pointed list on the left, atmospheric carbon, I just want to talk about that a little bit because you notice you don't see it listed in any of these possible feedstocks here. But it is the most tantalizing, and I think the one that, especially in Europe, we're seeing a lot of focus and a lot of hope placed on being able to start from atmospheric carbon, basically carbon dioxide, and use that as the primary feedstock for sustainable aviation fuel. So I just wanted to, because that's going to come up as we go through the process, as we go through this presentation, I just want to talk a little bit about it here. So it is technically feasible. We know how to do it. We have processes that can make that happen. And basically what they do is they're able to take the carbon dioxide, they're going to put it through a process that I don't pretend to fully understand. They're going to convert it to carbon monoxide and use that, essentially combine it with hydrogen gas, use that as a syngas feedstock that can be used it can be used in a couple different processes. The Fischer-Tropsch is the most common feedstock, or the most common process that can be used using the atmospheric carbon feedstock. The atmospheric carbon can actually be converted also into alcohols, so it can also be used as a feedstock for the alcohol to jet pathway as well. So we'll talk a little bit more about that as we go through, but I just wanted to point out the fact that it is technically feasible. Why isn't it being developed more today? Why aren't we seeing, more of it? And the reason is economics, not surprisingly. The benefits from using atmospheric carbon as a feedstock, and that's known as power to liquid, either PTL or ESAF, depending on who you're talking to. But these ESAF fuels are fantastic in terms of greenhouse gas emissions. They give us, at least theoretically, the highest potential for greenhouse gas reduction percentages. But the difference is at this point, it's very, very energy intensive. The processes are very energy intensive, which means that the cost of generating power to liquid or ESAF fuels is on the order of about 3 times more than other types of SAF, which makes it about 9 times more expensive than standard petroleum-based fuel. But the hope is that with additional technology, additional development of green energy, additional refinements to the process, that's the hope, is that these atmospheric carbon will ultimately be the feedstock for sustainable aviation fuel.
Hi, so my question was, are there any life cycle analyses done for the 8 of these processes done?
So the short answer is yes, there have been. Thanks. I guess I should put it here so that stays search. Yes. I don't have the answer. I don't have those numbers with me, but yes, those numbers have been done, have been run. In general, they're going to come out between 50 and about 75 or 80% reduction of greenhouse gas. And again, I can't tell you standing here which is which, but those analyses have been done. And of course, you're going to have variation even within each category based on the feedstock that's used, the specifics of the processing environment, how far they're being transported. So there's going to be some variation. But yes, there are life cycle analyses that have been done. So we have at least baseline what these are going to be for each of these. The other thing I wanted to point out here before I leave this slide is maximum blend ratio, this column on the far right in this table. Right now, even though sustainable aviation fuels have been approved, they are actually being used in airlines today in very small quantities. The approval limits the blend amount, the percentage of sustainable aviation fuel that can be used in an aircraft. Right now, none of them are higher than 50%. And we'll talk about some of the reasons for that as we go through. I'm going to talk about some of the technical challenges that are being faced there, and we'll talk about why and how they're being overcome. So what does that mean in terms of where we are today? We know that right now there are 3 main commercial producers that are currently producing commercial quantities of sustainable aviation fuel. 2 of them are in the United States, and one is Neste, is an international organization. And we expect 3 more producers to come online in the United States just within the year 2024. So this is an area that's growing, and we've seen pretty dramatic impact from the Inflation Reduction Act, which went into effect in August of 2022. Most of you are probably familiar with it. We'll talk more about it as we go through. But we have seen a significant uptick in the production of sustainable aviation fuel just over the course of the last couple of years, as we can see on this chart. So this chart is showing the amount of renewable jet fuel, which is generally going to be sustainable aviation fuel, or at least a close approximation of sustainable aviation fuel in the United States. And these are data that we took from the Renewable Fuel Standard program. These statistics are reported by the government on a monthly basis. And you can see that just this year, 2024, these data only run through August. So that's 73 million gallons of sustainable aviation fuel or renewable jet fuel in 2024. That only represents about 2/3 of the year. So if you extrapolate that out, maybe figure about 100 million gallons of sustainable aviation fuel this year, 2024. And you can see how that's a significant increase over where we were just a couple of years ago. 2021, we're at about 5 million gallons a year. Just last year, we're at 26 million gallons a year. So we've almost quadrupled use of renewable jet fuel in the United States just in the last year. Again, if you go with me in the extrapolating out to the end of 2024, and we've multiplied by a factor of about 20 just in the last 3 years. So this is an area with huge growth, and this is happening on the ground, and we're, again, seeing more and more producers about to come online. So this is something that's happening in real time, and there is real success happening in the real world. That said, This is where we're planning to go. The federal government, in its SAF Grand Challenge, has set a goal of achieving 3 billion gallons of sustainable aviation fuel, or using 3 billion gallons of sustainable aviation fuel by the year 2030. That's 6 years from now. The good news is, if you do the math and you say, okay, in the last 3 years, we've increased production or increased use by a factor of 20. We do that for the next 2 3-year cycles to get us to 2030. We're at 40 billion gallons, which would be fantastic, right? That would way outshoot that goal. The problem is nobody is projecting that that's what's going to happen. So these are projections, and again, projections are inherently, right, unreliable to an extent. And these are projections that I've pulled from different organizations. The Energy Information Administration has a projection out to 2025, which suggests that the amount of SAF that's used will be about double what it is in 2024. And again, these charts are coming from different places, and the units change, so you can't look at the units necessarily. But if you just look at the percentage increase, talking about approximately double from 2024 to 2025. And then McKinsey, which is a private consulting organization, projects that between 2025 and 2030, we'll see an increase by a factor of about 5 again. So, based on these projections, again, if you kind of meld them all together and do some magic over them, you can guess that, these projections would show about a factor of 10, an increase of about a factor of 10 between 2024 and 2030, which only gets us to about 1 billion gallons, which is obviously 2/3 short of the 3 billion gallon goal. But lots of question about that. And I'll say this on an anecdotal, not statistical. I don't have any graphs to show here. Again, the work that we do, we spend a lot of time in a lot of different areas, in the energy transition, solar, wind, you name it. And there's a lot of, I don't want to use the word pessimism, but there's just a lot of frustration, I think, in a lot of those industries that feels very different in the SAF space. In the conferences that I've gone to, the people I've spoken to, the people from FAA that are heavily involved in this, the people that are administering the Ascent program, there's optimism. They truly believe that we're going to get to 3 billion gallons by 2030. Obviously, there's an election coming up in a couple of weeks that may affect that, and there are any number of other impacts that could change that. But I will say, just anecdotally, there is what I perceive to be genuine optimism that we're going to get to 3 billion gallons by 2030, despite these projections.
Who are the players in this industry? Like all those companies that are building these facilities and refining the fuel, are they the same players that we've seen from Exxon or Shell, or are they totally new entrants? Like who are the ones that are profiting from these? Who are these groups?
Thanks. I don't have a full roster to speak to that, but we're seeing a mix. There are some organizations that are strictly renewable energy based, biofuel producers that focus, that have been focusing on renewable diesel, and they're sort of expanding into sustainable aviation fuel, or have been developing sustainable aviation fuel, and are starting to see that increase. But there are, I think most of the major petroleum companies have a foot in the door here, and I think they're sort of testing the water, right? You see Phillips 66 is planning to open a plant later this year. I know Shell is involved. They're, again, not to this level, not to the point where they're ready to open a plant, but Shell has done some work on this. I believe Chevron has as well, BP. So it's a mix, but the oil industry is definitely a player, if not the biggest player at this point. Okay, so I want to talk at least quickly, in the interest of time. I think we have about 20 minutes before we get to the Q&A, about some of the obstacles that we're facing. And I'm not going to spend a whole lot of time on the first two, just because it's not the focus of what we're talking about, but I think it's important to give the full picture. The first set of obstacles are technical obstacles. And this is the reason for, on that slide a couple minutes ago when I was talking about the maximum blending percentages being limited to at most 50%. This is the reason that we have a maximum blending percentage at this point. And at the beginning, I said sustainable aviation fuel is nearly identical to Jet A petroleum fuel. Nearly identical, yes. Identical, no. And one of the main differences between sustainable aviation fuel, as these processes create sustainable aviation fuel, and traditional petroleum-based Jet A fuel, is the presence of aromatic compounds within the fuel. And those of you remember from your undergraduate chemistry classes, aromatic compounds are ringed compounds with the alternating double and single bonds, or at least that's how they're represented. It doesn't necessarily have a huge impact in terms of the energy quality or the energy that's being generated from the fuel, but it does have a pretty significant impact on two aspects of the properties of the fuel itself. One is the dielectric constant, which is a property related to the conductivity of the fuel. Why do we care about that? It's because when you think about an airplane and you think about the way we would have to measure, just gauge, think about your gas tank, right, in your car, the amount of fuel that's left in the tank. How do we measure that? In a car, we just use volume. We can't do that in an airplane because, right, we know that volume changes significantly with changes in temperature and pressure, and airplanes are up and down all the time. Temperature and pressure is changing all over the place, so we can't use volume alone. So what we have to do is try to measure mass. Again, I can't tell you that I fully understand all the mechanisms behind this, but in order to estimate the volume of mass, to figure out how much fuel is left in the plane, they use a combination of measuring volume, something else, and the conductivity of the fuel, which means the dielectric constant is important for that. And the presence of aromatics in the fuel is important for that as well, right? It helps create the dielectric constant. It helps us to know how much fuel is left. So again, bottom line is, using processes that I can't tell you that I understand, the aromatic composition, the concentration of aromatics in the fuel is important to that. So that's why, that's one of the reasons that we haven't quite gotten to the point where we can use 100% SAF in commercial airplanes at this point. The other thing, somewhat similarly, is O-ring seal swell, right? Again, these aromatic compounds, as you go through a jet engine, there are a number of what I envision to be essentially gaskets, right, that sort of close off one part of the engine from another, keep things tight, keep the fuel all where it's supposed to be. Aromatics help those rings to swell a little bit to sort of fill the space in between some of these connections. And again, without any aromatics, or at least a much, much smaller quantity of aromatics in the sustainable aviation fuel, they're not able to do that as effectively. So this is an issue that they're working on from a technical perspective. And I can tell you that, again, this is being studied. They're working on developing renewable sources for aromatic compounds. And this is a process that's being studied through the Ascent project that we talked about before by people who are much smarter than I am. And that's about all I think I'm qualified to say about it. And I may have even gone farther than I should have. The next set of challenges that I'm going to talk about are feedstocks. And again, I don't want to spend a whole lot of time on this, but I think most of you can appreciate the fact that when we're talking about transitioning from petroleum-based feedstock to renewable feedstocks, much of which is going to come from biomass, you can appreciate the fact that when we're talking about a scale of creating something on the order of 3 billion gallons of SAF by 2030, 35 billion gallons of SAF, which is the goal for 2050, you can appreciate the fact that that's going to require significant volumes of some sort of feedstock. And if you're talking biomass, right, that can create all sorts of other, we're starting to compete with food, we're starting to compete with other processes that can create problems for us. Important thing to know is that right now, I mentioned this before, but the HEFA process, hydrotreated esters and fatty acids, they're the only commercially available SAF today. We talked about the fact there are 8 different ASTM approved pathways. The only one that's really that's been commercially matured enough to produce large volumes of SAF is the HEFA process. And so, most of what you saw with that curve that I showed, the increase from 5 million gallons to 100 million gallons this year, almost all of that is HEFA, comes from the HEFA process. The HEFA process uses oils and fats as its feed source. So for the most part, what they're using are waste oils, vegetable oils, things like that. A lot of these processes are excluding food grade oils just for sustainability purposes and trying to prevent competition. But again, the bottom line is the feedstock is an oil and fat-based feed source. The problem with that is even though it's allowed us to, it's matured quicker than some of the other processes and it's allowed us to get to where we are today, we are going to hit a cap essentially on what's available in terms of feedstock. One estimate I've heard is that if we're talking about trying to achieve 100% SAF by 2050, we can only achieve approximately 6 to 8% of that using the HEFA process due to the feedstock here. And again, there's some variability in that going forward, right? We're developing more energy crops that can be used to produce oils that can be used for this. It's possible that will change over the course of time, but basically we need to do something to think about how to get from where we are today to the goals that we've set between even now 2030, 2050. I'll say long term, again, as I mentioned before, the hope is that we'll be able to use gaseous carbon, right? The power to liquid processes that we talked about before. The hope is that we'll be able to use gaseous carbon as the primary feedstock. That saves us from having to worry about quantity of oils, saves us from a number of other problems, but that is years off, probably decades, when I'm saying years, just because of, again, the cost. There's a huge energy cost associated with that, which has the risk of creating emissions through the energy generation process, and also there's just an economic cost to it. So right now that's the long-term goal, but we're decades away from that, I think it's fair to say. So for most of these other processes that we're talking about, one of the primary feedstock is going to be biomass. It's going to be, again, it could be any number of different types of biomass. It can be cellulosic biomass. It can be some of these energy oils. It can be, a number of different areas, but it's probably going to have to come from biomass, which of course means crops on the ground, plants. So this is obviously an area that people are aware of. This is something that's been studied. And earlier this year, even though it's described as the 23 billion ton report, this came out in March of 2024. Thank you, government, for the truth in advertising here. But the 2023 billion ton report did an analysis. And again, they're trying to figure out basically what's the bottom line? What is the maximum amount of biomass that we can produce? What's the maximum amount of biofuels that we can produce? So they, again, I'm not going to get into a whole lot of the specifics here, but they basically determined that in the United States, we can generate between 1.1 and 1.5 billion tons of annual biomass production once the market is fully matured. And that would constitute the equivalent of about 60 billion gallons of renewable carbon liquid fuels, which includes not only SAF, but renewable diesel, a number of other things. So again, the report did conclude, recognizing that sustainable aviation fuel is one of the primary uses of this, the report did conclude that we are able to satisfy over 100% of the projected demand for airplane fuel in the country. And just a reminder again, but when we're talking 60 billion gallons, the anticipated full amount of airline fuel, jet fuel that's going to be needed by 2050 is about 35 billion gallons. So this is not quite double, but it's almost double again. So theoretically, it's possible to get there. And just talking about some of the assumptions made in this report, the report does, again, recognize that there's going to be the potential, at least, for competition among food, feed, fiber. And so that has been sort of calculated into this and into the models that they run. They say that this includes establishing energy crops on less than 10% of U.S. agricultural lands. It also assumes an increase of timber production by about 15% with no decrease in forest land, no net decrease in forest land. So again, the competition that we talked about, that at least in theory is built into these models. So this is considered a sustainable level of biofuel production without having a significant impact on our ability to produce food and other crops necessary for the economy. I'm not going to spend much time on this, but this is, if you want to dig down into the report, this shows you where some of that's going to come from. The yellow bars at the bottom, that's where we are today. That's the biofuel production today. And if you look at how they build it out in the future, it's showing where they think some of these things are going to come. This additional energy is going to come from. But of course, as with so many things in the world, the biggest obstacle is just the economic impact of this fuel. We mentioned before, right, and I've thrown this out there, but right now, SAF costs about 3.5 times as much as traditional petroleum-based Jet A. So how are we going to convince the market to move forward with sustainable aviation fuel? And I think one of the biggest answers, I think the short answer is through policy. And that's the hope, is that we're going to be able to incentivize production, start to develop economies of scale that will naturally reduce the cost of fuel as we move into the future. But in the meantime, it's going to be law and policy that's going to help to get us from where we are today to where we want to be. And again, that policy is happening, as we'll talk through, that's happening on basically all levels: international, federal, state, and even regional levels. So this is happening all over the place. I've broken it down, some of the policies we're going to talk about today, I've broken it down into 5 different categories that sort of generalize the different approaches that are being taken by different government bodies. Again, with the goal of trying to increase SAF production and try to incentivize SAF production. This is just a quick chart before I get into those categories. These are all United States federal government statutes, policies, programs, something that are designed to incentivize the production of biofuels. And again, SAF is just a subset of biofuels generally, but you can see that the federal government has taken quite a bit of action broadly. I'm not going to talk about all of them specifically as we go through, but just to show there's a lot out there. But the categories I'm going to talk about are mandates, which are, as you would expect, right? Traditional command and control, thou shalt, do X, talk about some of those. Talk about direct government investment, which is primarily the approach that's being taken in the United States today. Favorable loan terms, we'll talk about that. That's kind of a mix of government and private incentives. We also have several policies that are actually pretty effective in the United States that, although there's no specific mandate in the space of aviation fuel, it does create an incentive, a private incentive to invest in those fuels. And we'll talk about how those work as we go through. And then I just have a catch-all for additional policies. So let's start by talking about mandates. Internationally, there are a couple of these out there where there are specific requirements from government or government-like bodies requiring something that that increases the production of sustainable aviation fuel, or at least incentivizes it. The first we're going to talk about comes from, again, the International Civil Aviation Organization, ICAO. I mentioned this before. This is a subset of the United Nations anyway, and one of their committees developed what's called the CORSIA system. It's the Carbon Offsetting Reduction Scheme for International Aviation. CORSIA, if you've spent any time working in this space, you've probably heard of that before. And basically what it is it's a program that's designed to offset any aviation emissions from international flights above what was supposed to be 2020 levels, but has now been set at 85% of 2019 levels. But so basically, if you're an airline that's operating in a country that participates in the CORSIA system, if you're operating international flights, any of those flights, and those flights produce more emissions than 85% of the 2019 level, you have to do something to offset those emissions. Generally, you're going to have to pay for offsetting programs, et cetera. Or one of the other things you can do, is reduce those offsetting obligations by using sustainable aviation fuel in place of jet fuel. So ICAO has, and this is pretty interesting, and if we had more time, we could dig down deeper into it, but CORSIA actually set up a very complicated, very broadly themed definition of sustainable aviation fuel. In the United States, a lot of what we focus on with sustainable aviation fuel is just reduction in greenhouse gas emissions. Under CORSIA, that's part of it, but they also look at a number of other social and environmental factors. And in order to qualify as a sustainable aviation fuel to reduce your offsetting obligation under the CORSIA system, you have to check all 14 of these boxes. And again, you can see what they are. The one thing that's worth noting is that under CORSIA, the greenhouse gas emissions, which again, when we think about sustainable aviation fuel, tends to be the biggest thing we're thinking about, the greenhouse gas reduction that they're requiring is only a 10% reduction, as opposed to most of the other programs we'll talk about today are much higher than that. And again, in the United States, we tend to think of 50% reduction as being the minimum threshold. The European Union also has an emission trading system, and this works, again, pretty similarly to most of the cap and trade systems that you're familiar with. There's an overall cap on the amount of CO2 emissions from a number of industries. It includes aviation. And if you're going to exceed that, you're going to have to buy credits from somewhere else, et cetera, et cetera. So there's an economic incentive to reduce the amount of emissions you have. Under that program, the use of sustainable aviation fuel is considered to be zero emissions, even though, in fact, it's not. It's considered zero emissions for the purpose of this program, which, again, reduces the obligation on the carriers, which strongly incentivizes the production and use of SAF. The EU also has what's known as the Refuel EU Aviation Program. And that program, again, it's designed to work differently, and it actually sets a minimum percentage of aviation fuel that's required to come from sustainable aviation fuel. And you can see that that's an amount that increases over time. It starts at 2% in 2025 and goes up to 70% in the year 2050. You'll see they also break it down between just broadly considered sustainable aviation fuels and what they label synthetic fuels. And the synthetic fuels here are basically the power to liquid fuels that we talked about before. These are fuels that are, using atmospheric carbon as the feedstock for the carbon in the fuel. And so you can see that this is a very clear attempt to create a driver, to bring down the cost and to try to incentivize the use of these power to liquid processes that right now are very far from being economically feasible. The United Kingdom, which we know post-Brexit is no longer part of the European Union, even though I still forget that sometimes. So they're not part of the EU policies that we just talked about, but they have their own policy it operates somewhat similarly to the Refuel EU policy that we just talked about. So they set minimum percentages of sustainable aviation fuel that has to be included as part of any jet fuel that's being used. And their program, again, also sets not only minimum percentage from a power to liquid pathway, they also set a maximum percentage, a decreasing maximum percentage over time that can come from the HEFA process. And if you remember, again, the HEFA process is the one that uses oils and fats as the feedstock, which we know we're not going to be able to scale up all the way to anywhere near 100% of the SAF we need. So again, you can see the UK here trying to drive transition to power to liquid and away from HEFA process, while also generally increasing the amount of sustainable aviation fuel that's being used across the board. Singapore also has a mandate, and they're approaching it much differently. They're actually imposing a levy that they're adding directly to passenger ticket prices starting in 2026. The idea is that they're going to create enough income to allow them to purchase enough SAF to constitute 1% of their total jet fuel use by 2026 and increase that to between 3 and 5% by 2030. Very different system there, obviously. And I think part of the reason Singapore is approaching it that way is just because of the amount of international travel that they have coming in through their airports. So they kind of view this as a way of getting other people to pay for their SAF, which may be harder to do in other places with more domestic flights or higher percentage of domestic passengers. So how about mandates in the United States? There's not much. Those are creepy looking crickets. I wanted to find a less creepy picture, but that's what I found, and that's what it is. But as you can imagine, for policy and political reasons, we haven't really seen much in the way of mandates in the United States. On the other hand, we are great at domestic or direct government investment. We are great at spending money to throw at this problem. So what we're talking about with direct government investment, just generally, these are policies where the government either directly pays for SAF research, technology, development, something like that, or it's providing subsidies to private parties who are producing those materials. The first category, and again, there's a lot here that we could spend a whole lot of time on, but the federal government has a number of SAF subsidies. The first category are FAST grants, and FAST stands for Fueling Aviation's Sustainable Transition. That's what FAST stands for. But these are grants that have been given to people to either develop SAF or part of the SAF development process, or to develop new technologies that may help to create a more economic development for SAF in the future. These grants were just awarded in August of this year, and you can see where they are across the country. They sort of span the country, and obviously there's more information online if you're interested. In addition, the Inflation Reduction Act includes several tax credits that can be used to reduce the effective cost of generating and developing SAF across the country. The two most directly related are the Blender's Tax Credit, which is in effect this year, the SAF Producers Tax Credit, which is in effect for the next 3 years from 2025 to 2027. Without getting into the details, basically it provides an incentive of up to $1.75 per gallon of SAF that's being produced that the producers can get back as a tax credit. So it effectively reduces their cost by $1.70, up to $1.75 a gallon. The systems work slightly differently between this year and then the one that will be in effect for the next couple of years, but I don't have time to get into those details. In addition, there are tax credits for producing clean hydrogen. Again, generally hydrogen that meets the definition, a sustainability definition of reduced greenhouse gas emissions. And there's also an incentive for carbon oxide capture sequestration credit. Carbon dioxide is the way most of us would think of it. But CCS, carbon capture and sequestration, is just, again, taking carbon dioxide that either is in the air or would be emitted into the air, capturing it, collecting it, injecting it underground for permanent storage and keeping it out of the atmosphere. So there are tax credits there. There are ways that some of these stack, some of them don't, but there are ways that any of these can be used to effectively reduce the cost of producing SAF. And they're part of the reason that I think we're seeing an uptick in production. There are also states with a number of SAF initiatives legislatively, and this is a project that one of our law students has spent quite a bit of time working on over the summer and fall. So credit to Mary Johnson for a lot of this research. But these are states that have some initiatives. We made this presentation to a lot of SAF people a couple weeks ago, and they said, "That's great. We love the research. Thanks so much for doing it. Don't let this slide see the light of day." Their fear is that this suggests that there's a lot happening at the state level, and there are a lot of state level incentives that are being created. And in reality, yes, all of these states are doing something, but some of them are fairly small. So not necessarily huge incentives coming through these, but still worth mentioning at least. But I wanted to at least add that caveat. So there are several states that have direct subsidies that, again, they operate differently from each other, but general idea is that they're going to provide some sort of tax incentive, usually in the form of a tax credit, to either the producer or the user of SAF. Again, they operate slightly differently in every state, but there are 6 states that have those. The federal government is also funding a number of research and development programs. Ascent, the program that we're involved in that I talked about at the beginning, being one example, but they've also given a number of other development grants, and then the national labs are also working on these programs as well and doing research. Oops. The next category, favorable loan terms, right? One of the challenges that industry is facing here is, especially because of the short term on some of these government tax incentive programs related to SAF. Remember, again, a lot of the Inflation Reduction Act programs, if you followed that at all, a lot of the tax credits go out 10 years. The SAF program only went out 5 years. So right now, it only goes through 2027. So some of these industries are having a hard time, some of these producers are having a hard time generating capital to invest in some of these projects because banks are looking at it and saying, wait, you're producing something that costs 2.5 times what its competitor does. You have these tax incentives, great, but they're only guaranteed for another 3 years. And, with political upheaval, who knows if they're even guaranteed for that. So there are, some challenges there. So there are some government programs that are designed to sort of help fill that gap, at least to a small extent. The Department of Energy Loan Program Office has a Title 17 Innovative Energy Loan Guarantee Program. This wouldn't apply to all SAF production facilities, but it would apply to production facilities that use new or innovative technologies. And these can be pretty substantial. They can go up to loans of up to $100 million and up to about 80% of the project cost. There are also industrial revenue bonds, at least for SAF processes that use waste as the feedstock. These are bonds that are essentially, the way the process works is these are bonds that are essentially given to, at least nominally, to local governments who then pass these bonds through to private corporations. And it sounds shady, but it's all above board, it's legal. And by virtue of the way the process operates, it essentially creates just a lower interest rate for these projects. So again, more favorable loan terms for some of these projects, as long as it can be considered a solid waste disposal facility. The next category we'll talk about are incentives for private investment. And these are actually pretty significant here. We'll talk about two different programs, and I realize that we're running short of time, so I don't have a lot of time to spend on them. But the first one is one of the longest standing biofuel programs that's been in place on the federal level, and it's called the Renewable Fuel Standard Program. So many of you may have heard of this or at least come across it in the work that you've done if you've spent any amount of time in this space. But basically what it does is sets a minimum amount of renewable transportation fuel to be sold in the United States every year. Aviation fuel technically isn't obligated. It's not part of that necessarily, so it's not obligated to compensate, but it is considered an opt-in fuel, which means if you're using a renewable fuel like sustainable aviation fuel, you can essentially get credit for that to the extent that it falls within one of the categories here. You can get credit for that. You can then sell those credits to someone who's producing a type of petroleum-based transportation fuel that has an obligation to offset some of its carbon emissions. So essentially, this does create the opportunity for sustainable aviation fuel producers to capture some of the value, to capture some money from through this program, basically from other parties that are obligated to offset some of their emissions. There are a number of states that have clean fuel standards, which in some ways they operate somewhat similarly, where the state sets a threshold that certain parties have to meet, and then if they don't meet that criterion, they have to buy credits from another private party to offset their excess emissions. California's is the one that's most mature. It's been in place for the longest. Basically, what it does is it sets a target carbon intensity of the overall fleet of transportation fuels that are used in the state of California. They set that target, and then it declines over time. You can see that in the chart in the center of the table here. So anyone who's producing fuels in the state to be used in the state of California that has a carbon intensity that's higher than the threshold that's been set for a given year, that creates a deficit that has to be offset by a credit. Credits are going to, of course, come from fuels that are generated and used and have a carbon intensity score that's lower than the threshold. So again, it basically creates a market by which if you're generating fuels with low carbon intensity, you can then sell some of those credits to traditional petroleum-based generators who need it to meet their obligation here under the clean fuel standard. Again, right now, similarly to the RFS, aviation fuel doesn't create deficits here. It's exempted from the program, but it can opt in and it can create credits. So it doesn't create as much of an incentive for sustainable aviation fuel as it would if it were not excluded from the LCFS program, but it does still create a financial incentive under the program. Other states, Oregon, Washington, and New Mexico have all adopted clean fuel standards that operate on the same general principle, although slightly differently. And New Mexico's actually was just signed this year into legislation, so their program actually hasn't started up yet, so we don't know all of the details about that program yet. Additional policies, the SAF Grand Challenge, again, we've talked about the fact that the government has set goals, 3% or 3 billion gallons of SAF by 2030, 35 billion by 2050. That's all part of that. And again, it's basically a whole of government approach to try to address this problem. Ascent, I think, it now falls under that umbrella as well. The last thing I'll talk about today, there are these disclosure requirements, and this is basically just an information disclosure obligation. Both the Securities and Exchange Commission at the federal level in the United States has established a policy requiring publicly traded corporations to disclose a certain amount of information about their climate mitigation efforts, as well as their Scope 1 and Scope 2 greenhouse gas emissions. That's going to be going into effect in the next, right now it's being challenged, it's being litigated right now, but assuming it survives the litigation challenge, it will be going into effect in the next couple of years. California also has a corporate data disclosure policy, which is in some ways broader, in some ways narrower than the SEC policy, but again, it's going to require disclosure of information about climate mitigation measures and greenhouse gas emissions. So I think that's basically all I have. I mean, I think the takeaway from this whole presentation is that the aviation industry, it is an industry that's difficult to decarbonize, but it's also an industry that has started to recognize that it needs to take some steps. And we're starting to see some really strong indications that this is starting to take off in the commercial sector, right? We're starting to see some real growth in the industry. Right now, it's still far, far short of where it needs to go, but just looking at where it's been over the last couple of years, it is pretty remarkable when you consider how much has happened. There are a number of technical, financial, economic challenges that will need to be overcome over the course of the next few years. If it's going to grow to meet the net zero goals that industry and governments have set for 2050, and I think some of the policies that we've seen are policies that will help get us there. Whether they're going to be sufficient is another question. And I don't know that I would say I'm confident that this is enough, but it's at least a start, and we'll see where things go from here. So with that, it's 10 after 5, and if anybody has any questions, I'm really excited about getting to throw this box again. So questions, comments, thoughts?
I'm wondering if there's slightly more optimism in this space, in part because it strikes me as just an inherently international industry, more so than many, because aviation is itself so international. And it was interesting to see the international aviation organizations that you mentioned several times. I wonder if there have been any comparisons between this and, say, progress in other heavy freight, like trucking or whatnot, and whether the international collaboration should create more hope. But maybe technologies and policies are being shared more regularly globally or not.
Yeah, I think that's probably right. I think, again, and what you're saying has a lot of value and a lot of merit, because I think a lot of the initial conversations happened, like you said, at the international level. It happened at ICAO. And then some of that sort of bled down. I think one of the other factors that I would say here, maybe as opposed to some of the other industries, is that it's a smaller industry overall that's providing services to, generally speaking, higher income clientele. So I think a lot of those factors come into play too, where it's a little bit easier for them to coordinate and maybe not feel as concerned about the economic impact it's going to have. But I think you're right.
Particulate pollution similar between SAF and today's jet fuels?
So that's a great question. My understanding is that in general, it's a little bit less It's, it's not, we're not talking the order of 50 to 75%, but it's at least a little bit less just because of there are fewer impurities because of the way it's created. But to the extent that we're going to have to try to retrofit some of these fuels to address the technical challenges I talked about with the aromatics, once we start introducing some of those, it could actually offset some of the gains, the reductions. And so long term, we'll see what it looks like. But my understanding right now is that there is some at least marginal improvement in some of those things, but that may disappear basically as the fuels are maturing.
And is this being developed by itself as an aviation, or is it part of a larger transportation, considering alternatives like trains and maybe Zeppelins one day?
So the programs we're talking about here, the programs are well, most of them are designed and geared specifically toward airlines and aviation. Some of the federal programs I talked about are geared toward biofuels more generally. So that would bring in some of these other transportation fuels. But I think this is the focus primarily of the aviation industry and regulators of the aviation industry. That said, there is a lot of overlap because there's the chemical processes used to develop sustainable aviation fuel are similar to the processes and really the end product of renewable diesel. So there winds up being a lot of overlap. The producers we're talking about, there are a lot of producers that are thinking right now they're developing renewable diesel, which is a much more mature industry. But there's a lot of consideration of, hey, maybe if the financial incentives shift, maybe we'll take some of that renewable diesel and shift it over to sustainable aviation fuel. So there's definitely a lot of interaction in that space. Nice.
So one of the major problem in biofuels is the direct and indirect land use change.
Mhm.
So as our demand is growing and our agricultural land is limited, so how do actually we approach to solve that?
Yeah, and that's a huge challenge, right? And there's, I think the federal government's approach is, the study that I talked about before, the billion ton report, it's trying to account for a lot of those factors, it's recognizing the need to use, the need to not create pressures for deforestation or creating pressures that are going to reduce the amount of housing that's available or pressures that are going to drive up the cost of food. They added several constraints to their model to try to account for that. And, they're still saying that even with those constraints, there shouldn't be a significant concern about direct and indirect land use changes. And even with that, they're still thinking that there's enough biomass available to generate 60 billion gallons of biofuels. That said, what happens in a model is not what happens in the real world, right? And that's one of the concerns that's out there, and I think it's a legitimate concern, and we'll see what happens in time. And I think that's part of the reason that you're seeing European governments trying to incentivize the drive, shifting ahead to these power to liquid fuels where we're going to use gaseous carbon as a feedstock, so we don't have to rely as much on biomass. But I think the best thing I can say is that it's a major concern. People are aware of it, but we're going to have to see how things play out.
Well, thanks to everybody who came to this, and thanks to everybody on Zoom. If you want to stick around and ask Mike some more questions, that would be great. But thank you very much. Thanks, Mike.
Thank you.